Hello students, today we are going to discuss from this session about the previous year question paper, that is the chapter Dual Nature of Radiations and Atoms and Nuclei. Let us start, children. Yes students, from the chapter Dual Nature of Radiation from Atoms and Nuclei, let us see. Define intensity of the radiation on the basis of the photon picture of light and write its SI unit. See, the amount of light energy or photon energy incident per meter square per second is the radiation on the basis of the photon, and the SI unit, which is Weber per meter square, or we can say Joule second meter square. Joule per second meter square. The second question is, the graph shows that the variation of stopping potential with the frequency of incident radiation for two photosensitive metals A and B. Which one of the two has higher value of work function? Justify your answer. You see the graph, child? Now they have given in y-axis, that is the stopping potential. For two metals we have to compare. So which one of that has higher value of the work function, you must know. So the work function formula first. Work function W naught, which is equal to H nu naught. So here from the metal, and that the frequency of the incident radiation with the x-axis and y-axis, they have given stopping potential. Both are which is in the directly proportional, right? So the metal A and metal B, observe it. By that you may understand that we have taken V naught 1 is greater than V naught. From that you can say that metal A is higher potential, higher work function. Right? So next question. The given graph shows the variation of the photoelectric current versus the applied voltage of two different photosensitive materials and for two different intensities of the incident radiation. Right. So identify the pairs of curve that correspond to different materials, but it should be the same intensity of the incident radiation. See, they have given the graph. If you observe, you may observe the graph. You may understand that this is for the electric y-axis, which is their current, electric current. And this is for the applied voltage. Right. So they have given the photosensitive material which given two different intensities. So these are all one curve and this is another curve. Right. Now you must know about which are all the pairs of curve. See, it should be to the different material, but it should be the same intensity. It's very important, children. So the intensity should be same, and the different materials, for the different material you should be safe for it. Understand? So this will come under, see, observe 1 and 3. The 1 and 3 will come under that. So these are the two graphs, that is the different materials from that and same intensity, right? And we can give the curve 2 and 4. Observe 2 and 4, that both are same intensity. Right. So the question is, define the term stopping potential in the relation to photoelectric effect. So by relating the photoelectric effect, we can say stopping potential is the minimum negative or retardation potential of anode for which the photocurrent stops or it will becomes zero. Right. The second question, a monochromatic source emitting light of wavelength 600 nanometer has a power of output 66 watt. Then you have to calculate the number of photons emitted by the source in 2 minutes. So here you can write the formula which is equal to energy of one photon. Energy of one photon E which is equal to hc by lambda. So E which is equal to 6.6 into 10 power minus 34 standard value. C that is also 3 into 10 power 8 whole divided by that lambda value which is equal to 6 into 10 power minus 7. So these are all the standard value that they will provide in the question paper itself. By seeing it you can write, right? So E which is equal to hc by lambda. So that is equal to, we can write 3.3 into 10 power minus 19 joule. So this is the energy of one photon. Okay. Now here you can write it E1 which is equal to, that means the first energy 1, that is 66 joule. So that here the number of photon in 1 second. So number of photon in 1 second, right, N which is equal to 66 by energy is what? 3.3 into 10 power minus 90, right? That is equal to, by simplifying this you will get N into 10 power 20, sorry 2 into 10 power 20 N value. So N which is equal to 2 into 10 power 20 is the first second. So what it will be? The total number of photon which is emitted in 2 seconds, right, by this source of 2 minutes, not 2 seconds, 2 minutes. So the total number of photon that is emitted by the source in 2 minutes, N which is equal to N into 2 into 60. So that is equal to 2 into 10 power 20 into 120. So that we can write 2.4 into 10 power 22 photons. Right. So the question is, the equivalent wavelength of a moving electron has the same value as that of a photon having an energy of 6 into 10 power minus 17 joule. You have to calculate the momentum of the electron. For that, you must know about first E which is equal to h nu, energy which is equal to h nu. We can write hc by lambda, right? So that from this we can write lambda which is equal to hc by E. Is it right? So lambda which is equal to hc by E. From the base formula we get it. So that the wavelength of the moving electron lambda which is equal to hc by E, right? So we can say from this relation momentum P which is equal to h by lambda, that is equal to he by hc, right? he by hc, so which is equal to E by c. So momentum P which is equal to, from the above relation we got it E by c. So by applying E value and c, the speed of light, we will get the momentum value now. So P which is equal to, E value is what? 6 into 10 power minus 17 whole divided by 3 into 10 power 8. The SI unit kilogram meter per second. So you will get, by simplifying this, 2 into 10 power minus 25, yes, minus 25 kilogram meter per second. So this is momentum, the value for the momentum. So the question is, show that the radius of the orbit in hydrogen atom varies as n square, where n is the principal quantum number of the atom. See, you have to show that the radius of the orbit in hydrogen atom varies as n square, but n is the principal quantum number of the atom, right? So first you have to write mv square by r from the centripetal force, the formula which is equal to 1 by 4 pi epsilon naught into n square by r square. And from this derivation, we can get mv square r, which is equal to 1 by 4 pi epsilon naught into e square. Okay. Here, mvr, which is equal to nh by 2 pi. So, we can relate mvr, which is equal to nh by 2 pi. From this, we will get m square v square r square, which is equal to n square h square by 4 pi square. Can we write like this? Right. Then we will get mr, which is equal to n square h square whole divided by 4 pi square into, instead of that we can write 4 pi epsilon naught by e square. Right. Instead of that r value we can apply here. Right. So from this derivation, we can take the r value, that is the radius of the orbit in the hydrogen atom, which is varies, they have given as n square, where n is the principal quantum number of the atom. So r, which is equal to r, which is directly proportional to n square. R we can write r, which is equal to kn square. From the above relation, we got the value of r, which is equal to kn square. And the next question is the diagram. The figure shows that the energy level diagram of the hydrogen atom. Now we have to find out the transition which results in the emission of the photon of wavelength 496 nanometer. See the electron emission, which is n, which is equal to 1, n which is equal to 2, n which is equal to 3 and 4. For categorized energy level diagram they have given, hydrogen atom. So now the energy E1, which is equal to what is the value, minus 13.6 electron volt, and the E2 value which is equal to minus 3.4 electron volt, and we can say that E3 and E4 value also, E3 which is equal to minus 1.5 electron volt and E4 which is equal to minus 0.85 electron volt. So from this we can get H, which is equal to 6.6 into 10 power minus 34 standard value, we know that, and H value. So here this one 3 into C value is 3 into 10 power 8 whole divided by, they have given the photon of wavelength 496 nanometers, so 10 to the power of minus 9 into 1.6 into the electron value 1.6 into 10 power minus 19 electron volt. So by simplifying this, you will get the H value which is equal to 2.5 electron volt. So the question is, write two important limitations of Rutherford model which could not explain the observed features of atomic spectra, and how were these explained in Bohr's model of hydrogen atom. Here you can use the Rydberg formula to calculate the wavelength of the H alpha line. That is, we can calculate it. First we will see the two important limitations of the Rutherford model which could not explain the atom spectra. See, the first point says that it would be a spiral into the nucleus. That means it loses its energy, we said. See, electron which is moving in a circular orbit around the nucleus, so that it would get accelerated. So therefore that only we are saying that it would be the spiral into the nucleus. And it must emit continuous spectra only. Because of, according to Bohr's model of hydrogen atom, we can say the electron in an atom that can revolve in certain stable orbits without the emission of the radiant energy. And also we can say the energy is released when released as well as it may be observed only when an electron jumps from one stable orbit to another stable orbit. So this results the discrete spectrum. Right. So we are calculating the wavelength of the H alpha atom, that is a H alpha line, 1 by lambda, which is equal to R into 1 by 2 minus 1 by 3. So we can say, which is equal to 1.1, the R value 1.1 into 10 power 7, 1 by 4 minus 1 by 9. Okay, so 1 by lambda, which is equal to 1 by R into 2, 1 by 2 square by 1 by 3 square. So that only we got 1 by 4 minus 1 by 9. So this is the base formula, right? So from the base formula we are calculating. Now by simplifying this, the alpha value which is equal to 656.3 nanometer. So this is the lambda value, right? And B part of the question, using Bohr's postulate, obtain the expression for the radius of the nth orbit in the hydrogen atom. Here, mv square by r power n, which is equal to 1 by, what is the formula? 4 by epsilon naught into E square by R square. So, Rn, which is equal to E square by 4 pi epsilon naught E square, is the first formula. I can take it as for the R, right, radius. Now, mvr, that is nth orbit, nh by 2 pi. See, we want that the Bohr's postulate obtain and expression for the radius of the nth orbit in the hydrogen atom. So that Vn, which is equal to, from this, nh by 2 pi mr. So from this above relation, you can get r value, the radius value, nth orbit r value, which is equal to E naught, epsilon naught, n square, h square by pi me square. So this is the hydrogen atom, which is nth orbit, the radius of the nth orbit in the hydrogen atom. The question is, define the terms mass defect, binding energy for a nucleus, and the relation between the two. That means the relation between the mass defect and the binding energy. For a given nucleus reaction, the Be nucleon per nucleon of the product nucleus or nuclei is more than that for the original nucleus. So as this nuclear reaction is exothermic or the endothermic in nature, we have to justify the answer. The points first we can say for the definition of mass defect and the binding energy. The mass defect of any nucleus XZA, that is the mass number, and as the difference of the mass of the nucleus and the sum of the masses of its constituent nucleon, which we can say that del m, that is mass defect, which is equal to m dash minus m, that is equal to z m naught plus a minus z mn minus m. So this is the formula for the mass defect. We can say that is z mp plus a minus z mn minus m. So m dash abbreviation is z mp plus a minus z. Where mp and mn, we can say that the mass of the proton for mp and mn is the neutron, mass for the neutron. For the binding energy, we can say that binding energy is the energy which is required to separate a nucleus into its constituent nucleons. So the relation between the binding energy and the mass defects Be, which is equal to mass defects C square. That is the relation between that binding energy and the mass defects, we can say. The next question they have asked about the energy, which is the reaction, nuclear reaction is the exothermic or the endothermic. See, actually that reaction is a exothermic reaction, right? Because of the increasing in B curve, binding energy per nucleon, which implies more mass has been converted into the energy. So this would result the release of energy. So this is the exothermic energy. Now draw a plot of B by A, that is binding energy curve, versus mass number A for 2 which is less than 1, the mass number A is less than 170. Use this graph to explain the release of the energy in the process of nuclear fusion of the two nuclei. See, you are seeing this, the curve, that is B by A curve, that is binding energy per nucleon versus mass number. So this curve gives the different range of the binding energy nucleon. The energy released, how the energy released in the process of nuclear fission and the fusion, that can be explained. See, from the above curve which you are seeing, we can say that when a heavy nucleus breaks into two medium-sized nuclei, that is, we can say the nuclear fission, the B by nucleon per nucleon, which increasing the result of the release of energy. And also from that we can show that when two small nuclei combine together to form relatively bigger nucleus in nuclear fusion, as we know, that is B by, that is binding energy per nucleon increases, the resulting the energy will come. So this shows that the binding energy per nucleon is getting increased when the energy will get released. Draw a plot showing the variation of the de Broglie wavelength of electron as a function of its kinetic energy. So that you have to draw the kinetic energy versus lambda. So kinetic energy which is in the x-axis, and in y-axis you can draw lambda. Then the graph will be for the de Broglie wavelength of graph of electron as a work function, which you can say that it is proportional, inversely proportional to the kinetic energy with the lambda. You will get the graph, the shape of the graph like this, and write the relation of a de Broglie wavelength which is associated with the particle of mass m in terms of its kinetic energy. Then the relation lambda, which is equal to, we can say E whole divided by root 2m E. Okay, lambda which is equal to, you can say that h by root 2m E. That is the relation of the de Broglie wavelength which is associated with the particle of mass in terms of the kinetic energy. Yes, children, we have learned from this session, from the chapter Dual Nature of Radiations and Atoms and Nuclei. We have discussed so many various types of questions, graphical representation, graph-based questions, the experimental various types of questions we have discussed. Practice well. Thank you, students.